Okay, in this example, we're told we have an isolated system of total mass m, and it consists of two equal masses of the same liquid. Both, the liquid's assumed to be incompressible, has the same specific heat, and the only difference is that the two liquids have different initial temperatures. So we're given that liquid 1 has an initial absolute temperature T1, liquid 2 has an initial absolute temperature T2, and they're equal masses, so each liquid has a mass of 1/2 m at the beginning. Then what happens is we remove this partition that separates the two liquids so that they mix. We have a total mass of m, and we achieve some final equilibrium temperature. So part A of this problem is to determine the amount of entropy production in terms of the variables mass, specific heat, and the initial temperatures. And then part B is to demonstrate that sigma, this S should be a sigma, should be positive. Okay. So the way we'll get started with this is we're going to use the entropy equation, since we're trying to find the amount of entropy produced. And that entropy equation is going to be applied to a control volume that surrounds the liquids in the container. Okay, so this is really the same control volume, just at different times. So we'll write out the entropy equation. I'll write it out in full. Okay, so there's our entropy equation. We'll go ahead and use some assumptions and some information about the problem to simplify this. First of all, there are no inlets and outlets. It's a rigid box. It's isolated from the surroundings, so those are zero. So there's no inlet, no outlet. Because the system's isolated, there is also no heat transfer, so that's also zero. No heat transfer. Again, because the system is isolated. And then, so then we know that the entropy production is equal to the change in the entropy for the whole system. The change in the entropy is going to include the change in the entropy for liquid 1 and the change in the entropy for liquid 2. Right, so we'll go ahead and evaluate those. Now remember that the liquids here are both incompressible, so the change in entropy for liquid 1 is going to look like the following. It'll be the mass of liquid 1, which is 1/2 m, times its specific heat, which is C, times the natural log of the final temperature over the initial temperature. So this is assuming an incompressible substance and a constant specific heat. Right, so that goes back to our incompressible substance model and determining how what the change in entropy is for an incompressible substance. We have the same situation for liquid 2. There the mass is 1/2 m, same specific heat, and then we'll have the natural log of Tf over T2. The initial temperature for liquid 2 is T2. So we'll just add those together, and we'll get in the end is the following. So that's what our entropy production looks like in terms of those variables. I'll just go one step further. Since we have two natural log terms that are added together, you can actually rewrite that a little more compactly as the natural log of Tf squared over T1 times T2. Just a more compact way of writing that. So that's our entropy production for this situation. Okay. Now, part B, so that's part A. For part B, we're asked to determine or demonstrate that sigma, the entropy production, must be positive. Okay, so to do that, what we're going to do is I'm going to take it a little bit, a slightly different approach, and I'm going to say if the entropy production is positive, what conditions must I have for the temperatures, just to, and then show that that's indeed the case. So I'm going to work it a little bit backwards here. First of all, let me just rewrite the sigma. I'm going to go ahead and divide through by the 1/2 mass times the specific heat. All those quantities are positive, so I'm just rewriting that equation a little bit differently. So in order for the entropy production to be greater than 0, in fact, what I'm going to do is I'm going to set it greater than or equal to 0, because if it's equal to 0, then it's reversible. If it's greater than 0, then it's irreversible. For that to happen, what must the conditions on TF and T1 and T2 be in that particular case? So in order for that to be true, then the TF squared over T1, T2 has to be greater than or equal to 1. Okay. Before I go any further, let me just take a look at what the final temperature is going to be for this particular scenario. So we know our initial temperatures. Let's find the final temperature. To find that final temperature, I can use the first law applied to that same control volume. So I'm going to go to the first law for a moment here. Let's go ahead and write that out. So we'll write it out in its full glory here. Again, we know that there's no inlet, there's no outlet, there's no heat transfer because it's isolated, there's no work because it's isolated, it's a rigid container, so we're left with the change in the total energy is 0, but the change in total energy is a change in internal energy plus the change in kinetic energy plus the change in potential energy. We'll neglect any changes in kinetic or potential energy. The box is not moving around or changing elevation. So we have the change in internal energy is equal to 0. Change in internal energy is going to be comprised of the change in internal energy for system 1 plus the change in internal energy for liquid 2. The change in those internal energies will be the mass times, okay, so the mass of, the mass of system 1 times the I'm sorry for a moment here. Yeah, so times the specific heat times the change in the temperatures. So that's delta U1, and then we have the same situation for liquid 2. And again, that's using the incompressible model in constant specific heat. So those are the assumptions going into that. And we can combine those things together. And then what you'll find is the final temperature is the average of the two temperatures, of the two initial temperatures of the liquid. So we know what the final temperature is in terms of the initial temperatures by using the first law. So what I'm going to do is I'm going to take that final temperature and I'm going to substitute it back into the expression that we had from the entropy equation. So let me go ahead and do that. So if I substitute that in, the numerator will be 1/2 squared, so that makes it 1/4, T1 plus T2 squared, all over T1 times T2 has to be greater than or equal to 1. So again, I'm combining the entropy equation and first law expressions together here. So let me go ahead and expand that out. We'll have T1 squared plus 2, T1, T2 plus T2 squared greater than or equal to 4 times T1 times T2. So I'm just doing some algebra here. That'll give me T1 squared minus T1 times 2, I'm sorry, there's a 2 there, plus T2 squared greater than or equal to 0. That'll be T1 minus T2 squared has to be greater than or equal to 0. So let me just we have this expression here. So let me just go back and tell you what we've done here. What we did is we took a look at our expression for the entropy production. We substituted in for the final temperature because we used the first law to find that. And then what I said was, okay, under what conditions what conditions must I have for sigma to be greater than or equal to 0? What must occur there? And so that's what I've done down here. So this expression is what we must have in order for the entropy production to be positive or equal to 0. So you can see right away, if T1 is equal to T2, what will happen then is you'll get sigma is equal to 0. The entropy production will be equal to 0. And this is our internally reversible situation. Basically what happens is, since it's the same liquid, you remove the partition, nothing really happens. The temperature doesn't change. It's just the same temperature. You just have the same liquid just sitting there. So nothing's really happened there. But if T1 is greater than T2, then when you look up in the expression here, you'll get a positive number, square it, that's still positive. So in that particular case, sigma will be greater than 0. And that will give you an internally irreversible process. So if T1 is greater than T2, then it'll become internally irreversible. Similarly, if I make T2 greater than T1, we'll get a negative number here, but we're going to square it, and that'll also be positive. So if T2 is greater than T1, we'll also get sigma greater than 0. And that will also be internally irreversible. So we've now shown that the only situation where sigma is equal to 0 is if T2 is equal to T1, then it becomes internally reversible. But all other scenarios, whether T1 is greater than T2 or T2 is greater than T1,